You finish downloading a page, the connection closes cleanly, and both sides are satisfied it is over. And yet one of the sockets stubbornly refuses to disappear for a full 2 minutes. This is your socket, the one that lingers. On the other end is the peer, the machine you were talking to. Closing a TCP connection is a polite, mutual affair, and understanding who lingers means watching exactly how these two say goodbye to each other. The state your socket enters is literally named time wait. It is not stuck or broken. It is deliberately holding position, running a timer set to roughly twice the longest a packet can survive in the network. The first reason for the wait hides in the very last message. The final acknowledgement your side sent might be lost in transit, and if it is, the peer will be left hanging, unsure whether the connection ever truly closed. If that happens, the peer does something reasonable. It resends its FIN, asking again to close. But that only helps if your socket is still around and able to answer, which is precisely what time wait guarantees. The second reason is spookier. An old, delayed duplicate packet from this very connection could still be wandering the network, and it must be given time to expire before its ports are handed to anyone else. Because once the wait ends, the payoff arrives. The port and the connection's whole identity are released, free to be used again by something new without any fear of confusion with the past. But that reuse is exactly where the danger would live if the wait were skipped. Let us follow one connection through its final handshake, into time wait, and out the other side to a safe reuse. The close is a 4-step dance. One side sends a FIN meaning it is done sending, the other acknowledges, then it sends its own FIN, and finally the first side acknowledges that. 4 messages, 2 FINs, and 2 ACKs. The side that transmits that very last acknowledgement is crowned the active closer. In our story, that is your socket, and being the active closer is precisely what obligates it to wait rather than vanish. So instead of freeing itself immediately, your socket transitions into time wait and starts its timer. The connection is functionally over. No data will flow, but the socket entry stays alive in the system's table. Now picture the first hazard playing out. That final ACK you sent gets lost somewhere on the path. From the peer's viewpoint, it sent a FIN and heard nothing back, so as far as it knows, the close never completed. So the peer retransmits its FIN, politely asking to close all over again. This is normal TCP reliability at work, but it only rescues the situation if someone is still listening on your side to receive that repeated request. Because your socket is parked in time wait, it is still there to catch the resent FIN and reply with a fresh ACK. Had it closed instantly, the peer's retransmission would hit a stranger and trigger a confusing reset instead. Now the second hazard, the stranger one. Networks can delay and duplicate packets, so a segment from this connection, sent minutes ago, might still be crawling along some slow path, only to be delivered late. Imagine you immediately opened a brand new connection reusing the exact same pair of ports. That wandering old packet could arrive and be mistaken for valid new data, silently corrupting the fresh conversation. This is why the timer is set to twice the maximum segment lifetime, the famous 2 MSL. It is simply long enough that any straggling packet from the old connection is guaranteed to have expired and been discarded by the network. While it waits, the socket is not idle dead weight. It is actively guarding that 4-tuple, the pair of addresses and ports. Nothing else may claim that exact identity until the timer runs its full course. At last, the 2 minutes elapse. The timer fires, time wait ends, and the socket finally closes for real. The local port and the full connection identity are released back to the system, cleanly and completely. Only now is it truly safe to reuse that same port pair for a new connection. Every old packet has died, the peer has long since finished closing, and there is nothing left to confuse the newcomer with the ghost of the last one. So the linger you resented was never laziness. It is a careful quarantine that keeps a lost acknowledgement recoverable and a stale packet harmless, protecting the very next connection from inheriting the last one's mess. The trouble is scale. A busy server that actively closes thousands of connections a second accumulates a mountain of sockets in time wait, and each one is holding an ephemeral port hostage from a strictly limited pool. The best cure is architectural, arrange for the client, not the server, to be the active closer. Then the time wait burden lands on many scattered clients instead of piling up on one heavily loaded machine. Options exist but demand care. Features that allow reusing a port still in time wait can help when applied correctly, while blunt tricks that recycle sockets aggressively have caused real, subtle breakage and are best avoided. The honest takeaway: never just switch time wait off to make a number look better. It exists to defend correctness, and the right move is to close from the client side and let the state do the quiet job it was designed for. So the full picture. The active closer sends the final ACK, enters time wait for twice the packet lifetime so a lost ACK can be re-answered and old duplicates die out, and only then releases the port for safe reuse. That's the whole trick. Next time you see a pile of connections sitting in time wait, remember they are not stuck. They are standing guard for 2 minutes so the next connection starts clean. Follow how it all runs for more. See you next time.